We will now use the information that we have to explain the spectroscopy of atoms, firstly hydrogenic atoms, but also many electron atoms. Well, we know that the energies of the hydrogenic atoms are given by this equation. This is the general energy equation. That's n squared. So basically the principal quantum number n determines energy. So when we have a transition from an orbital defined by quantum numbers n1, l1, ml1 to a lower energy orbital with quantum numbers n2, l2, ml2, we know that the change in energy is equal to delta E. And this excess energy is given off as a photon according to the Bohr frequency condition which we have defined earlier, where delta E is equal to h nu. Now one might think that any type of transition is possible from any orbital to any other orbital, but this is not true. A photon has an intrinsic spin angular momentum of 1, so S is equal to 1 for a photon. We've said this before. And the change in angular momentum of the electron must compensate for the angular momentum carried away by the photon. So this has to be taken into account when we consider the transitions that are possible. So for example, if you have an electron in a d orbital with L equal to 2, it cannot make a transition to an s orbital with L equal to 1. Now in the same way, an electron in an s orbital cannot make a transition to another s orbital because there would be no change in the angular momentum to make up for the angular momentum of the photon leaving, because in an s orbital L is equal to 0 and in another s orbital L is equal to 0, but the change in angular momentum must be 1 for a photon to leave with angular momentum, so that also doesn't make sense. So the result of all of this is that some spectroscopic transitions are allowed and some are forbidden. And we use a rule which is called a selection rule. And that rule states which transitions are allowed and which are not allowed. So for a hydrogenic atom, the selection rules are as follows, and this is the most important one. The change in L can be plus or minus 1. Note that there is no selection rule that includes the quantum number n, the principal quantum number, because this does not affect the angular momentum. So let's have a look at an example where we apply these selection rules. The question asks, to which orbitals may the 4d electron make a transition to? So if we look at the 4d electron, it has a value of L equal to 2 for a d electron. And we know the selection rule says the change in L can be plus or minus 1. So the final orbital must have L equal to 3 or L equal to 1. So that would be a p orbital or a d orbital. So any p orbital, sorry, that should be an f orbital, or any f orbital. L equal to 3 is an f orbital is allowed, provided that the change in ml is 0 or plus or minus 1. So this 4d electron cannot make a transition to any s orbital. There are diagrams known as Grotrian diagrams, just be aware of this, that indicate allowed transitions using lines, and the thickness of the lines indicate the intensities of these transitions in a spectrum. Okay, we now move on to many electron systems. Up to now we've looked at hydrogenic atoms, which are one electron systems. And now we are moving to many electron systems. So if we were to look at the example that we're talking about, we have a nucleus and we have more than one electron surrounding the nucleus. So how do we describe this atom quantum mechanically? So firstly, our Schrödinger equation becomes very complex. Why? Well, firstly, you have interactions between each of these electrons and the nucleus that you have to take into account. But you also have interactions between all of these electrons. So the number of interactions that you have to take into account is very complex, and this is a dynamic system. These electrons are moving the whole time. So even with helium, or for helium, which has 2 electrons, there's no analytical expression for the Schrödinger equation. So we cannot solve the Schrödinger equation exactly even for helium, which has just 1 electron more than hydrogen. What do we have to do? We have to start making approximations. And we use the information that we have for the hydrogenic atoms in these approximations. So when we look at the quantum mechanical description of this many electron system, instead of having one wave function describing the whole system, which would be very complex, we imagine each electron to occupy its own orbital, and we use the orbital descriptions that we obtained from the hydrogenic atoms. So each orbital that an electron occupies is the same orbital that we obtained through the hydrogenic atoms, like the 1s orbital, 2s orbital, etc. So in the orbital approximation, that is what this approximation is called, suppose that a reasonable approximation is obtained by thinking of each electron as occupying its own orbital. So in the orbital approximation, this overall wave function that contains the coordinates of all the electrons is approximated by putting each electron in its own wave function, which looks the same as the hydrogenic wave functions. So each of these orbitals are similar to the hydrogenic orbitals, but what happens in this case is that the nuclear charges are changed a little bit because of the presence of the other electrons in this atom. So we can now move to what is called the Aufbau principle, where we start adding electrons to orbitals. And this is something that you are familiar with, so most of this I want you to do as self-study. We know for the hydrogen atom the electron configuration is 1s1, helium 1s2, then we get to lithium, we've got 3 electrons, but according to the Pauli principle, the third electron cannot join the first 2 in the s orbital, it has to go to the p orbital. So the Pauli principle tells us that no more than 2 electrons may occupy a given orbital, and their spins must be paired. This is something you know already. And then when we go to the second shell, the question is, when we go to lithium, does the next electron go to the 2s or the 2p orbital? Because remember, in the case of the hydrogenic atom, we said that 1s, 2s, 2p, these 2 orbitals have the same energy, they are degenerate. So the question is, are they still degenerate? And this brings us to the concepts of penetration and shielding, which is also self-study. I will just quickly recap, because what this means is that or this concept explains basically why these orbitals are no longer degenerate. So if you look at a many electron system, you find that the energy levels look like this. So the s orbital has a lower energy than the p orbital, has a lower energy than the d orbital, lower than f. So if we were to look at the second shell, so 2s, 2p, the third electron will definitely go to the s level and not to p, because s has a lower energy. Now why are they degenerate in the hydrogenic atoms, but in the many electron atoms they are not degenerate? And this has to do with penetration and shielding. So if this is the nucleus and this is your many electron atom, you can imagine this electron, which is a bit further from the nucleus. If there were no other electrons present, this electron will feel the attraction of the nucleus. But in this case, there are other electrons present. And you can imagine this to be a fire, and these are people standing around the fire. So this person will feel less heat because these people are blocking the heat of the fire. In the same way, these electrons are blocking the nuclear charge from this electron. So this electron will feel a nuclear charge Z effective, which is smaller than the real nuclear charge. And this is called shielding, because these electrons shield this electron. And as a result of this, and also as a result of penetration, so if we look at the way the orbitals, or how close the orbitals are to the nucleus, we see that the 3s orbital, if we look at this figure, is closer to the nucleus than the 3p orbital. So effectively your 3s electron will be the one closer than your 3p. So that would be 3s, that would be 3p. So your 3s orbital will be less shielded. It's standing next to the fire. Your 3p electron will be more shielded. So as a result of these two effects, what we find is that the energy levels now are no longer degenerate in a shell, and they have this relative energies. So S, P, D, F. Okay, so you should be able to explain penetration and shielding. This is self-study. Look at these values. For example, in carbon, the nuclear charge is 6. The 2p orbital only feels a charge of 3.1. 2s feels a stronger charge of 3.2. That explains why it has a lower energy than the 2p, because that feels a stronger charge. So your positive-negative attraction is more, stabilizing it. Lower energy, stabilizing. Okay. That brings us to the building up principle, which is self-study. You know all of this already. We start with the bare nucleus of atomic number Z. So remember, that is the number of protons. We've said this before. And you typically start adding electrons to these orbitals. So just look at the position of those two orbitals. You're familiar with that. I just want to point out a few things in the notes. So when you have a scenario where you have 3 orbitals and 2 electrons, you put them in 2 different orbitals. You know this, and that is as a result of Hund's rule. which is a truly quantum mechanical property. And that rule says that electrons with parallel spin repel each other less. So we don't do this. We put them in with parallel spin. And that is known as spin correlation. We're going to see this term again. Spin correlation tells us that electrons with parallel spin repel each other less. So please remember that. So if two p electrons in the ground state of carbon have the same spin, we call that parallel spin. I also want you to focus on these exceptions that have been listed. Talking about the 3d and 4s orbitals. So calculations show that the energies of the 3d orbitals are lower than that of the 4s orbitals. However, when we look at scandium, we find that it has the following configuration. Other possibilities are so why this specific configuration? Because we know that orbital has a lower energy, so why do those two electrons not prefer to go to the lower energy orbital like in that case? Why do we find that that is the preferred configuration? Well, the reason for that is it has to do with electron-electron repulsion in these two orbitals. The 4s orbital is further from the nucleus than the 3d orbital. So if we were to draw a very crude picture, there's our 3d orbital, there's our 4s orbital. So if we put electrons in the 4s orbital, they would effectively be further from each other. They would have more space than putting the same electrons in a 3d orbital. And as a result of that, the repulsion is less in the 4s orbital than in the 3d orbital. And that energy gained by reducing the repulsion is more stabilizing than the energy gained by going to a lower energy orbital. So scandium would rather have electrons in the 4s than in the 3d orbital, which explains why it puts as many electrons as possible in the 4s orbital further away from the nucleus, lower repulsion, but it has to still put one in the 3d orbital. It doesn't put one only in the 4s, it puts two in the 4s orbital. So you should be able to explain the electronic configuration of scandium. Now let's look at vanadium. The rest you must please read in your own time. If we look at vanadium, the electron configuration is this, and if we look at vanadium 2+, the electron configuration is this. But if you look at the number of electrons for the scandium, which we said at that electron configuration, the scandium atom, and the vanadium 2+ ion, they have the same number of electrons, so they're isoelectronic. Sorry, ladies and gentlemen, that's fine, it's perfect. So why, if they have the same number of electrons, does scandium prefer that configuration, but vanadium 2+ prefers that configuration, which is equivalent to this one, which we said that scandium doesn't prefer? Because shouldn't they behave the same? They've got the same number of electrons. Well, the answer lies in the nuclear charge. Because the nuclear charge of vanadium, and we can refer to the effective nuclear charge, basically determines the electron configuration. So the nuclear charge of vanadium is higher than that of scandium. So your positive-negative attraction for vanadium is going to be much larger. So even though we now put the electrons in a higher energy, in a lower energy orbital but with more repulsion, you are going to get stabilization because of the positive-negative attraction. This is a much more positive nucleus than that of scandium because of the nuclear charge. So you should also be able to explain why this happens for vanadium and it doesn't happen for scandium. These exceptions are important. So please go through the details in your own time so that you are able to explain this. You can have a look at anions, and then the section on ionization energies and periodic trends of ionization energies, also self-study. This you have covered since first year, and what you should be able to do is explain the ionization energy trend in going from lithium to neon. You should be able to explain why it increases and why it sometimes drops and why there's a general increase, etc. And all of this is given in your notes in a lot of detail. You have done this in many other courses, in first year courses, so you should not have any problems. The textbook describes it in a lot of detail, but you should be able to explain this in detail.